Alright, so here's our third and final part of the Unit 10 slides of solutions and colloids. Let's talk about what electrolytes are. So solutes can be classified by their ability to conduct electricity. Electrolytes are solutions that, when they're dissolved, will separate into ions, which then can move around the solution and conduct electricity. If a solute dissolves and does not separate into ions, then they do not conduct electricity, and we call that a non-electrolyte. There are different levels of electrolyte. So a strong electrolyte is one where the solute dissociates completely, and some examples of that are NaCl salt or KCl, some of the stronger NaNO3, CO, Cl2, etc. A weak electrolyte is a solute that will only dissociate a little bit. So some of the salts like AgCl, PbSO4, things that actually precipitate, will dissolve just a little bit, and they'll be a weak electrolyte. And then there are solutes that do not dissociate at all, as we saw on the last slide, and those are molecular compounds like sucrose or ethylene glycol, which is what's in antifreeze, ethyl alcohol, which is the alcohol that we drink. And so these we call non-dissociated compounds, and they are non-electrolytes. So we're going to look at a colligative property. Colligative properties of solutions are properties that depend only on the concentration of the solute particles and not on the identity of the solute. And so as you can see, this will become important when we look at solutes that totally dissociate. So if you remember NaCl, we saw this just a minute ago, will break apart into two particles, Na and Cl. So if you put in 1 molar of NaCl, then the concentration of particles will be twice as big, or 2 molar. The three colligative properties that we're going to look at are boiling point elevation, freezing point depression, and osmotic pressure. So the boiling point elevation is one of the colligative properties. What is the boiling point elevation? Well, that means that a solution, the boiling point of the solution will always be higher than the boiling point of the pure solvent. So a saltwater solution will boil at a temperature higher than 100 degrees, the normal boiling point for water. So again, this is called the boiling point elevation. The amount that the boiling point increases is given the symbol delta TB. The triangle is the symbol for delta, which means change, and TB means boiling point, or the temperature of the boiling point. So delta TB is how much the boiling point increases for the solution. The boiling point increase will depend on the concentration, so the higher the concentration, the higher the boiling point. We can use the following equation to find the boiling point of the solution. So let's look at what each part of the equation means. The little I in the equation is the number of particles it dissociates into when it dissolves in solution. For solutes that are non-dissociating, little I equals 1. So that would be our ethanol, our ethylene glycol, sugar, things like that. For solutes that are strong electrolytes, little I depends on the solute. So NaCl has a little I of 2. Calcium chloride has a little I of 3. It breaks up into 3 particles. Na3PO4, remember that PO4 is a polyatomic, so that stays together, but that's 1, and then 3 sodiums for a total of 4. The Kb in the equation is called the boiling point elevation constant. It depends on the solvent, but since in this class we're only going to worry about water as our solvent, and so Kb will always be equal to 0.52. The M in the equation then is just molarity. The freezing point depression works a lot in the same way. The freezing point of a solution is always lower than the freezing point of the pure solvent, so depression, it goes lower. For example, salt water solution will freeze at a temperature lower than 0 degrees Celsius. And this is called the freezing point depression. So the amount that the freezing point decreases is represented by delta TF, F for freezing. The equation, as you can see below, is the same. The freezing point will depend on the concentration of the solute. The delta TF is equal to little I times KF times M. Again, little I is just the number of particles. M is the molarity. The only thing that changes is that the constant for water for freezing is 1.86. So let's look at an example. Alright, so what will the freezing point and boiling point be of an NaCl solution that has a concentration of 3.3 molar? Well, since it's NaCl, the first thing we need to recognize is that it breaks apart into two particles. So little I equals 2. So then, for the freezing point depression, Kf is 1.86, little I is 2, the molarity is given to us, it's 3.3, and so that means the freezing point depression will be 12.3 degrees. Now that's not the freezing point, that's how much the freezing point will be lowered from normal freezing, which of course is 0. So we subtract 12.3 from 0 and we find that the new freezing point of the solution will be negative 12.3. The boiling point elevation, we use the same I, the same M, but the constant changes, so it's just 0.52. So if we find delta TB, it's 3.4. Now again, that's how much the boiling point will be higher than the normal boiling point. So we add it to 100 degrees, the normal boiling point of water, and we find that it's 103.4 degrees is the boiling point of this solution. So what we've done in effect is we've taken a liquid and we've made the temperature range that it stays a liquid is larger than the original water. So water would be a liquid from 0 to 100, and now this solution will be liquid from negative 12.3 up to 103.4. This is one of the ways that we use, that's why we put salt on ice in the winter. When you put salt, what you're doing is you're making a solution, a salt solution, and what that'll do is lower the temperature so it will melt. It will freeze. It won't freeze until it gets much colder, and so it will melt. The salt that we put on ice is actually calcium chloride. That's that blue solution, or maybe it's copper chloride. I think it's copper chloride. Anyway, that's what lowers the freezing point, so it won't melt. I'm sorry, it won't freeze. So what will the freezing point and boiling point be of 275 grams of ethylene glycol in 1 liter of water? Well, ethylene glycol is non-dissociating, so that means that little I equals 1. But we're not given the molarity in this problem, so we need to calculate the molarity before we do anything else. 275 grams, we can convert that to moles. 275 grams divided by 62 grams per mole gives us 4.44 moles. And then 4.44 moles divided by 1 liter is 4.44 molar. So if we plug it into our equation, the freezing point depression will be 1 times 1.86 times 4.44, which is 8.3 degrees. Again, we subtract that from 0, and so we find that the freezing point for this solution is negative 8.3 degrees Celsius. The boiling point elevation, again, I is 1, 0.52 is the constant, M is 4.44, so that gives us a boiling point elevation of 2.3. If we add that to 100 degrees, we get 102.3. The last colligative property is called osmotic pressure. Before we can talk about osmotic pressure, though, let's talk about what is osmosis. There are certain materials that are called semi-permeable. That means they allow some things to pass through it, but not other things. So they'll allow, in this case, smaller solvent particles like water to pass through, but they don't allow the larger solute particles like sugar to pass through. So if you put a membrane between two different solutions that are different concentrations, the molecules of the solvent can move both ways. they can pass through the membrane. However, the sugar cannot. So what generally happens if you've got solutions of different concentrations is that the more dilute solution will start to, water will start to move into the more concentrated solution in order to dilute it down so that they can be more similar to each other. Well, when that happens, since it's only the water that can move, the left-hand side water, the whole solution will rise and be higher than the right-hand solution. So it's diluting it down, but also the water moves up. And so you see sort of a uneven volumes of liquid on the two sides of the membrane. Well, osmotic pressure then, if we were able to push the left side back down to go back to where it was originally, we'd have to, of course, put pressure on it to push the water back to the other side. The amount of pressure that we would have to put down onto that side is called the osmotic pressure. Another way to think of it is how much pressure do you need to put on the left-hand side solution so to stop osmosis from happening. Again, that's the osmotic pressure. So, again, the pressure needed to prevent the osmotic flow is called osmotic pressure. And again, osmotic pressure is a colligative property, which means that the number of particles is what's important. So we're going to use a term called osmolarity. Osmolarity is just where we take little I, the number of particles that it breaks apart into, times molarity, and we get osmolarity. So for example, if NaCl is 1 molar, and since NaCl breaks apart into 2 particles, then the osmolarity for a 1 molar NaCl solution would be 2 osmolar, or 2 osmol. A cell membrane is actually a semi-permeable membrane. So it acts like osmosis can happen into and out of our cells. It will let water, small solute particles pass, small solvent particles pass back and forth, but of course it won't let the big parts of the cell out. And so it's very important that our cell membranes have the same osmotic pressure as the solution. So if we put a cell in a solution, we want them to have the same osmotic pressure. In order for something to have the same osmotic pressure, that means they have to have the same osmolarity. So if two solutions have the same osmolarity, they will be isotonic, meaning they have the same osmolarity, and so they have the same osmotic pressure, which means that no osmosis will occur between the two solutions. So that's what we want. We want to put a cell, we want like our blood to have the same osmolarity as the cell itself. If we put a solution in our body that has a lower concentration than the cells, what will happen is that water will flow into the cells, causing them to burst. So if a solution has a lower concentration to another one, it's called hypotonic. And so we do not want to put our cells in a hypotonic solution because our cells will burst. A solution that has a higher concentration is called hypertonic. And so if we put our cells into a solution that is hypertonic, water will flow out of the cells, and eventually the cells will shrink, and this is called crenation. Now this is the same process that happens if you take a cucumber and put it in a very salty brine solution, which is much more hypertonic than the cucumber. All the liquid will flow out of the cucumber and it will shrink and you have a pickle. So let's look at an example. If you were to go to the hospital and given a saline solution, it would be 0.89% weight per volume. Saline solution, and that is isotonic with red blood cells, otherwise we wouldn't put it in our body. So what we want to figure out is what is the osmolarity of this solution. So what I'm going to do is I'm going to convert to the units, but in order to find osmolarity we need to know what molarity is, and then we multiply it by little I. So molarity, remember, is moles divided by liters. So what I'm going to do is convert 0.89 grams of NaCl to moles. So of course 0.89% means that there's 0.89 grams in every 100 mils. So if we convert 0.89 grams to moles by dividing by the molecular weight, we get 0.015 moles. And then we convert 100 milliliters to liters, which is the unit we need for molarity, and that's 0.1 liter. So if we want to figure out molarity, we take moles divided by liters to give us 0.15 molar. Now, just keep in mind, I'm not going to ask you to do a calculation like this. So just kind of, just sort of listen to what I say, and hopefully you can at least follow what I'm doing. You don't need to redo it. So the molarity of a 0.89% saline solution is 0.15 moles per liter. And then since NaCl breaks apart into two particles, osmolarity is 0.30 osmol. So we know that red blood cells then have an osmolarity of 0.3 osmol. So let's look at these solutions and figure out which of these is also isotonic to red blood cells. So of course, osmolarity depends on the number of particles that the molecule breaks apart into. So what we need to do is find the osmolarity of these solutions up above. So in A, so they're all Na2SO4. So SO4 is a polyatomic ion, so that stays together, and Na is two particles. So little I equals 3. So to find the osmolarity, what we need to do is multiply the molarity by the number 3, little I. So A would be isotonic to blood because 3 times 0.1 is 0.3 osmol. So a 0.1 molar Na2SO4 solution is 0.3 osmolar. The second one, which you might have guessed at first because it's 0.3, but since it breaks apart into 3 particles, is actually 0.9 osmolar, and so this would be a hypertonic solution. And C, 0.15 molar, since again we multiply by 3, would be a 0.45 osmolar. Of course, like we saw in the previous example, 0.15 molar NaCl would be isotonic because we would multiply it by 2. And just for your information, I won't ask you this either, but if you've been in a hospital, you've probably, if you're giving glucose solution, you say, well, a glucose solution is 5.4%. So how does that compare? Well, again, remember that 0.3 osmolar solution is what is isotonic to blood cells. So what I'm going to do is I'm going to convert 0.3 osmolar sugar back to percent and see what that is. So little I is 1 because sugar does not dissociate, and so a sugar solution that is 0.3 molar will also be isotonic with blood. So what I'm going to do is I'm going to convert 0.3 molar to percent. So I'm going to take 0.3 moles, convert that to grams by multiplying by the molecular weight, 180 grams. And that's where the difference comes in because the molecular weights of sugar and salt are different. So 0.3 moles is 54 grams of glucose. And then 1 liter is 1,000 milliliters. So to convert back to percent, we take 54 grams, the solute, divided by the solution, 1,000 milliliters, and we get a 5.4% solution. So a glucose 5.4% solution has an osmolarity of 0.3. A 0.89% NaCl solution, saline solution, also has a 0.3 osmolarity, and that's the same as blood. So other solutions would be figured out the same way. Blood has an osmolarity of 0.30, and so you have to put in a solution that is isotonic to blood. All right, so this is just to tie things up. I want to talk a little bit about the difference between a solution a colloid, and a suspension. So they're all mixtures, but what happens, the way they're different is that the size of the particle, size of the solute particle is different. So a solution has very small particles. They're less than 1 nanometer in diameter. A nanometer, of course, is 10 to the minus 9 meters. So they're teeny, teeny, tiny. Colloid solute particles are actually a little bit bigger. They kind of glom together, and so the particles themselves are a little bit bigger than one molecule. And so they are between 1 nanometer and 1 micrometer. They're a little bit bigger. You still can't see them with the naked eye, but they're definitely bigger. Now a suspension is a mixture where the solute particles are much bigger than 1 micrometer in diameter. And so in fact, they're verging on where you can actually see them. So this chart summarizes the 3 different mixtures. A solution has an appearance that's clear, transparent, and homogeneous. Colloids tend to be homogeneous, so they all look the same throughout, but they tend to be a little bit cloudy. And then a suspension is very cloudy, and in fact it's heterogeneous because you can see all the different particles. So like if I took a handful of mud and threw it in water, that would be a suspension. Blood is also a suspension because it's cloudy, it's heterogeneous. If you look now from the naked eye, you can't see differences in blood, but if you look through a microscope, you would see that there are different parts to it. A colloid, again, is homogeneous, and some examples of colloids are milk or fog. So it's homogeneous throughout, but the particles are bigger. So again, you can see the particle size. A solution is less than 1 nanometer. A colloid is between 1 nanometer and 1 micrometer, and a suspension is greater than 1 micrometer. And so what happens is if you shine light through a solution, the particles are so small that they don't reflect light, and so that's why it's clear and transparent. However, a colloid the particles are big enough that they will scatter light. If light shone into them, they will shine light back if they sort of reflect the light. And so this is sometimes called the Tyndall effect. So that's why colloids are cloudy, a little bit foggy. A suspension then is variable, but light is usually scattered because the particles are so big they scatter the light. So that's why they look very cloudy. Solutions, as I've said before, will not separate. So they could stand all day. A salt solution will sit all day and you'll never get the salt to separate. A colloid is the same thing. They won't separate. They'll stay homogeneous. But a suspension, like a handful of dirt and water, eventually will settle out, and so you'll just see the solid sitting on the bottom of the liquid. A filtration, similar. You cannot filter a solution, you cannot filter a colloid, but you can filter a suspension. You can get the muddy dirt and everything out. And so again, the examples, solution can be something like a salt solution or a sugar solution, whereas a colloid is something like milk or fog, and then suspension is like muddy water. One last thing I just wanted to talk briefly about is dialysis. A dialyzing membrane is a semi-permeable membrane, sort of similar to what we were talking about earlier with the colligative property. So they are osmotic membranes, but they're a little bit bigger than like a cell membrane, and so they allow the solvent molecules and other small molecules or ions to pass through. And so what happens is if you've got that dialyzing membrane, it will it keeps the blood from going through, but it lets the waste pass through, some of the smaller waste molecules to pass through. So you can see in this picture, the blood enters, and it enters into the dialysis machine. The fresh dialysate, the liquid, is kind of empty of any kind of waste, so it's much lower concentration. And so as the blood passes through, these waste molecules and some water molecules will pass through the membrane into the dialysate, or the less concentrated liquid. So the blood is more concentrated in the waste, the dialysate is less concentrated, so all those particles will flow through the membrane into the dialysate, and then it will be carted away, and then the blood is clean and returns back into the body. So similar to osmosis. And that's the end of this unit, so I hope that you have enjoyed it.